Emily?
Hi, I'm so sorry.
Oh,
I've been
that's
having issues with my phone all day.
okay.
I had to go get a new one.
I
And
figured
then
that there was
this
something
one's having,
going on when you didn't
yeah,
log
and then
in.
this one's having the same problems as the last one. I'm just like, oh my god.
No.
Ooh.
All right, so we got the results of your quiz back or the test on Chapter 9, huh?
Yeah, and that's actually better than I thought I did. So,
Okay, well, that's not bad. Question number 1, you have any questions about it?
no, I went through it and I figured that one out.
Okay, so the first term is this term right here.
Yeah,
Okay,
and then the next one.
what kind of series is this?
It's, oh, that one? It's a geometric series.
It is a geometric series, which means the only thing that determines its convergence is the value of what's in the parentheses.
Mm-hmm.
What do we need for it to be convergent?
It needs to be less than 1.
And it is. And so it's convergent based on the geometric series, and its sum is a sub 1 over 1 minus r. Or in this case, 4 is a sub 1, and 2/5 is r.
We got that 1.6 was a sub 1.
I'm sorry, what?
We got that 1.6 was a sub 1. When we went over it in class. When we went over that one.
Well, I don't think so. In other words, sums are just like integrals. That 4 I can remove and put out there. Okay? So now, the sum of this very straightforward geometric thing is 1 over 1 minus r, which is 1 over 3/5, which is 1.6, but we have to multiply it by 4. So it's actually 6.4, not 1.6. 1.6 would be the sum without the 4. And that's why I can put 4 in the numerator. I'm not sure what happened in class, but I'm pretty sure the sum of this is 4 over 3/5, which is 6.4.
Okay.
Okay? This one. We can express that number as right?
I see, yeah.
And so forth and so on. In other words, if we add these 3 numbers together right now, we would get so if I continue this series in this way, I will create what they're looking for, which is that repeating decimal. Now, how do we put this in a series? Well, that's a good question. A would be 378, and R
would be 1 minus 0.001, right?
R would be 0.001.
Yeah.
So now the sum is going to be 378 over 0.999. Why does that not seem right to me? What's wrong with that answer? It's basically 378. A was 0.378, not 378. It was 0.378. So that is an appropriate sum. That makes more sense. In other words, this thing should sum to a little bit more than 378. And this indicates that it does. That's slightly more than 378. Okay?
Sounds good.
Okay, let's go on to the next page. I haven't had a chance to look at this yet.
This one I guess.
You got this?
Kind of.
Let me just look at it for a moment. Oh, so you just did a Taylor series.
Yeah, but I didn't do the right one.
This means you didn't get credit on the problem?
It goes from 1 to a 4, so if there's a 4 next to it, I did it.
If there's a 1 there, you got 1 point. If there's nothing there, you got nothing on it, huh?
Well, he didn't give nothing. He gave 1 for almost all of it except for the last 3.
So what is wrong with 4? Is it the fact that we're not looking for a Taylor series, or is it the fact that you calculated your coefficients wrong? I noticed that what you came up with is not precisely that. That's an alternating series.
Yeah, and the way that we did it in class, because we only got through the first 4 in class, was we took the first series that it gave us, so 1 minus x plus x squared, so on and so on, and we put in x squared for wherever there was an x, and then we multiplied all of that by x to the 3rd. It's in the last picture that I sent you on one of the emails.
Which one?
Last picture.
I'm looking at the photo 3.
Oh, then maybe it's photo 1. I don't know where it is.
You only sent me 3.
I sent you 2 emails.
Oh, you did? Oh, well, I didn't look at the other email. Excuse me.
Oh, sorry.
No, I only got 1 email. Unless there's 2 of them. Well, no, hold on. I guess there are 2. I just didn't open the first one. Yeah, okay, sorry. My
no, you're fine.
Google Mail is, it's fooled me like that before. So let me think here. These are the same. Where can I put these? Put it here. Just for the moment. Whoops. What did I do? the same first page. How many pages am I supposed to have? 4 or
6?
6?
Yes.
They appear to be the same.
Oh no.
In other words, this photo too, maybe not. Yeah, it's the same questions.
Oh no. Alright, so...
Hold on, let me just open the third one. Yeah, this is 7, 8, and so...
Alright, let me try to send you.
Well, before you do, let's look at this problem here.
Well, there's 2 pages of more tests that I need to get used to.
Okay, well go ahead and do that while I'm looking at this.
Okay.
This, to me, looks like, oh man, this is such a hard chapter. If I don't visit it regularly, I forget everything that I've learned. Where is this going to be? In fact, your book doesn't have a lot about this, doing this. Let me get my other book. Just my other book goes into depth a little bit more, and it has a really good section on doing these kind of problems. Finding the power series for functions like this. Okay, let me go back. Alright, let's review something here. Maybe we can use this technique. Or else I'm just completely out in left field. But I think this is what they're after. If I want the power series for that function right there, I want to try to write this function in geometric summation form. So, in other words, I want to write it as a over 1 minus r. Well, if I tried to write this function as a over 1 minus r, I need a 1 right there. I don't have that. But if I divide both sides by 2, top and bottom, then I have 2 over 1 plus x over 2. You see where that equals this?
Yes.
Okay. And now, in order to put this into a over 1 minus r, I have to put a double negative in there. I have to put it 2 over 1 minus a negative x over 2. Now I have it in the right format. I have it in a over 1 minus r. I can tell what r is. R is minus x over 2, and a is 2. So that power series would be 2 times the geometric series minus x over 2 to the n going from 0 to infinity. So using that technique, I was able to take that. In other words, I could do the same thing there. I could make that 1 over 1 minus a minus x. And then my power series is minus x to the nth. And you get this series. In In other words, the series for 1 over 1 plus x is 1 over 1 minus a minus x. You see how I turn 1 over 1 plus x into that? And now I know what r is. R has to be minus x. So this series, 1 over 1 plus x, would simply be
1 minus negative x.
Don't need the 1. It's negative x to the n power. Okay, so I think that's the logic that they want us to take here, but maybe not, because I haven't done one that has x cubed over 1 plus x squared. Given that that is the power series for that, find a power series representation for this. Well, let's see. If I divide everything by top and bottom by x cubed, it's not going to help in the least bit. It's going to give me 1 over x cubed plus 1 over x.
I sent you how we did it.
Okay, good. Let me look at it.
It's the last one there.
Yeah. The last photo?
Yeah.
Let's see what happens when I try to put those on my... So here's my new... Oh boy. Okay. I think these are the 3 new ones. You said it was photo 3?
Yes.
No, that's 7 and 8. Let's look at photo 2. That's 4. Oh, that's it, isn't it? Except that doesn't show how you did it in class. Am I clicking on the wrong one?
I think so.
Yeah, I think so too. I think this is the one that has how you did it. Here we go. This is what I should be looking at? Yeah.
Yeah.
Oh, so this is all your work on that. Okay. Boy, you got 2 perfect here.
That's when we did it in class.
Okay. You didn't do this work before answering the test. Okay, I got it. Okay.
No, not at all.
All right, so there's 3. Okay, I see what's going on now. I see what's going on, how you did it here. So, what we really have here is x cubed times 1 over 1 plus x squared. So what I really need to do is find the series for that. Well, that's close to a over 1 minus r. In fact, if I put another double negative in there, I get 1 over 1 minus a minus x squared. So the series would be x cubed. I don't know if I can leave that out there. I don't think I can. I think I have to put it in there. But then this can be represented by minus x squared to the n. In other words, that's r. minus x squared? Is this what you guys did?
I think so.
Except, yeah, okay, so, hold on a second.
We just put in x squared wherever there's an x and then multiplied it all by x cubed.
Right, except it's not an x squared I want to put in, it's a minus x squared. Notice that you put in minus x squared as the second term.
Yeah.
Hold on, but that was because the photo said, given that, here, let me close this one out, I only need it open once. So given that 1 over 1 plus x is that, it looks like you used that series for 1 over 1 plus x squared. Oh, I see what you did. You just put in x squared. Okay, that's what you said, yeah. Are you sure this is the right answer? Is this what he, is that what he said?
That's what we were doing, so.
Who's we? Is it you and your classmates? Or?
Yeah.
Okay. Oh, I see why you did it that way. Yeah. This is the same way I'm doing it. In other words, I got that series on my own from 1 over 1 plus x squared. In other words, I didn't use their assumption. I took their series 1 over 1 plus x squared, put it into a over 1 minus r, and r turns out to be negative x squared. So all I got to do is represent the series with the x cubed inside, and there's r right there. And now, when I go through term by term, notice my first term is, when I'm going from 0 to infinity, this will be 1, because anything to the nth, the 0th power is 1. So I get x cubed, and then when n is 1, I'm going to have minus x to the 5th. When n is 2, I'm going to have plus x to the 7th, and so forth. So we really didn't need, we didn't need this information. Had you given me that right there, I could have come up with the series.
Yeah.
I guess it's a little bit easier if you know that that is that, then you can just substitute x squared for x wherever you see it. Yeah, that's one of the properties about series and stuff that's so useful, is that you can take complicated polynomials like this and represent them based on the fact that that is a power series for that. It's kind of like it's like, how do we integrate e to the x squared? You can't integrate that, but we know what the power series for e to the x is, and so we just substitute x squared wherever we see x. So the power series for e to the x squared is something like this, I believe. I don't know, I'm not looking at it right now, but so that's essentially what you're doing, is when you plugged in x squared for wherever x was. All right, let's go on. Did you get this? No?
Nope.
Now this is the one you should have done everything you did on the previous problem.
I know.
This table right here, the one I'm so fond of, this tabular listing like we did here,
Yeah.
that's what you want to do on this. So let's do it. Or is that the answer?
No.
Oh, okay. I don't think so.
Well, I already know what the equation for sine of x is, so can't I just plug in
2x.
2x?
Well, that's a good point. Centered at x equals pi over 4. So we're going to have a, see, this is the difference. You know what the Taylor polynomial for sine of x is, but you know it for x centered at 0, not for x centered at pi over 4.
Okay.
Okay? So if we figure it out, let's go through it. Shouldn't be too bad. And I still haven't figured out whether the order 3, does that mean to go through 3 derivatives?
We went over that in class. When it says order 3, it goes until it's like 2x cubed. And then when they ask for terms, it's just number of how many items there are.
So it's the first 3 terms of the Taylor polynomial?
So this one would be until we get to
Well,
just
okay. All right, I'll go ahead and list the third one because I'm still a little unclear.
Okay.
So there's the first 3 derivatives. Now we have to evaluate those at pi over 4. Well, the sine of pi over 2 is 1. F prime of pi over 4. The cosine of pi over 2 is 0. F double prime is minus 4. And F triple prime has got to be 0 also.
I think we have to go one more.
All right, well, let's try this and see. Oh, because I see we're going to only have 2 terms.
Yeah.
Because of the zeros, yeah. Oh, so that's how it works, huh?
I think so.
Okay, so we have our coefficients. 1, 0, minus 4, 0, and 16. So it's equal to f of x, which is 1, plus, and this is going to be x minus the coefficient times x minus pi over 4, but the coefficient is 0, so there's no second term. The third term will be minus 4 times x minus pi over 4 squared all over 2 factorial. Am I right?
Well, yeah.
Yeah, because the term that had the 0 coefficient would have been x to the 1 over 1 factorial. Okay, and then we're going to have another 0 term, and then we're going to have plus 16.
Wait, wouldn't that be to the third, to 3?
I think it's squared. In other words, if I go ahead and put all the terms in there, let me just do that for the sake of argument. we get 1 minus 0 times x minus pi over 4 to the 1 power over 1 factorial plus 4 times x minus pi over 4 to the 2 power over 2 factorial. The next term would be x cubed, but it's got a... Excuse me?
Whenever we do sine, the factorial and the power are always odd.
You mean in the series for sine?
Yeah.
Hold on.
It's because it starts at x.
Well, that probably is correct. Oh yeah, e to the x was 1 plus x squared over 2 factorial, yeah. Hold on. And cosine's always even, huh?
Yeah, sine's always odd and cosine's even.
But does that make the sine at 2x odd? Guess it would, if you plugged in 2x everywhere where you were normally going to plug in x. However, once again, you're always coming up with the series for sine of x centered at 0. I'm not sure it's the same if it's centered at pi over 4. I don't think it is. This is kind of proving that it's not. In other words, this 2x you have right here, that has the 0 coefficient that we came up with in front of it. There's the 1 corresponding to that. This would be plus 0 times x minus pi over 4 all over 1 factorial. It disappears because of the 0. Then, first non-zero coefficient we have goes with the x squared term. Hold on, I can check this real quick. Maybe I can't. Pull up Wolfram alpha and see if they will give us the sine of 2x and then wow. I don't have a pi over 4. Let's see what they interpret that as. Just two functions. I wonder if I say centered. Come on, it's got to have a sum here somewhere. I got everything under the sun here. Here we go. Unfortunately, it doesn't have my centered at pi over 4 in there. It didn't figure that out. So, more interpretations, yeah. That's not going to help. Well, tell you what. Let's do this for x equals 0 and see if we get the proper thing. In fact, I hate to take this much time, but let's just see if it makes a difference whether it's centered at 0 or So this is going to be minus sine x, and this is going to be minus cosine x, second and third derivatives. So the sine of 0 is 0. Notice the difference. It does matter whether you're centering it at 0 or pi over 4.
Okay.
The reason you're getting all odd terms is only because you're centered at 0. Notice the first term I got is 0. And the next term I'm going to get is 1. And the next term I'm going to get is 0. This is your constant first term. This is your first x term. So x minus x cubed over 3 factorial, that's the kind of series we're going to end up with, right?
Okay.
But when we center it at pi over 4, it completely changes all of these coefficients, especially the sine of 2x, because the sine of 2 times pi over 4 is 1. So that becomes 1, that becomes 0, this becomes 1 times minus 4, and so forth and so on. So I feel pretty good about this answer.
Okay.
Right there. I'm not certain. I guess we need a third term, which is going to be, let's see, this one disappears. So I've got 1 plus this, and the third term would be minus 16x minus pi over 4 to the 4th over 4 factorial. Now, so you're saying that I need one more?
No, that's it. But
That's it. In other words, the third order polynomial is 1 term, 2 terms, 3 terms, huh?
Wouldn't it be plus 16 though?
Yes,
Okay.
that is a plus there.
Just making sure.
Yeah, no, very good. Yeah. Okay.
Awesome.
Okay, so notice this is centered at 0. So we've got, our first term is going to be 5, not 1, because f of 0 is 5.
Yeah.
Our second term is going to be minus 3x over 1 factorial. Our third term is going to be plus 8x squared over 2 factorial, and so forth, just like she's written. Okay? Where's this plus 1 coming from? What made you put that plus 1 in there?
I have no idea. I thought that instead of taking where it was centered, it was always just x plus 1.
Okay. All right. That's where, yeah. That's a big key of understanding there, is incorporating the where it's centered at.
Yeah.
For both this problem and the last problem. So if we want to approximate what the function of point 4 is, I could plug in 0.4 for x and take as many terms as I want. Well, if I'm only going to use the third, then I would just use these 3. In other words, 5 minus 3 times 0.4 plus 8 over 2 times 0.4 squared should be the answer.
Okay. So I just put in 0.4 for wherever there's x. Got it?
Yeah, into the orange one.
Okay, let me write that down real quick.
It's the same way you would approximate the sine of 0.1. How would you approximate the sine of 0.1? What is the series for sine centered at 0?
Yes.
What is it?
Oh, centered at 0?
Uh-huh.
It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on.
Well, if we wanted to use the first three terms to approximate sine of 0.1, we would just plug in 0.1 for x. Now, the fact that it's centered, that this is the series centered at 0 is key. In other words, I would not want to use that series to approximate the sine of 0.9. I'm not near 0. It's only going to work well if I'm centered at 0. Well, I may have to take that statement back because sine is one of those magical functions that is the series, the radius of convergence is the entire number line. In other words, the series is an approximation for the sine of anything. I could use this to approximate the sine of 0.9. But what's important to know is that that series is centered at 0.
Okay.
And you get a different series if you center it elsewhere. Alright, what is this page? Photo 2? So we need...
Number 7 I don't need help on.
Okay.
Or 8A, just 8B.
Okay. Let me just look at 7 real quick. Okay, so that's what you did here, was took the known series and substituted minus x squared. I wonder if e to the minus x squared is the one that you can't, I know that you can't take the integral. You can't find an antiderivative of that. And that's what makes this so useful. But the thing is, I always see it with a negative sign. I wonder if e to the x squared does have an antiderivative.
It does. We did that in class.
Really?
Yeah.
Wow. It has an antiderivative. Do you know what it is? Is it something simple?
Sorry?
Is it something simple?
I can't remember it off the top of my head.
Okay. I can't even imagine how to go about doing that. Maybe using substitution where you let x squared equal u and you go from there?
I really don't remember. I just remember that we did it.
Okay. So this negative sign must be critical to making that so you can't integrate it, in which case you have to use the infinite series in order to integrate it, because we can integrate an infinite series. All right, so let's look at 8a and b here. The check mark means the ratio test is the correct thing to use?
Yes.
Okay. And it looks like you've got it set up perfectly. So what happens to this? You end up with n in the denominator. So where did 2n plus 4 come from?
Don't ask me.
Let's go through this math, this algebra here.
1 sec, sorry, I'm trying to copy down the first part on this page.
Okay, so let me multiply this out. And in the denominator, I'm going to have n plus 1, right? In other words, n factorial divided by n plus 1 factorial is n plus 1. In other words, 6 factorial divided by 7 factorial would be 1 over 7, not 6. So n would be 6, n plus 1 would be 7, so it's got to be n plus 1. Now what happens? Now we have still this. And I want the limit of this as n goes to infinity. Well, what's it going to be?
I don't know.
The highest degree in the denominator is n cubed. The highest degree in the numerator is n squared. So this thing's going to 0. I don't have to do any of this combination. I don't have to even worry about that. When you take the limit of a polynomial over a polynomial, you merely compare the highest degree. If it's the same, if I had an n squared and an n squared, it would be the ratio of the coefficients would be the limit. But as long as my higher degree is in the denominator, it's going to 0. If I had an n to the 4th in the numerator, it would be going to infinity. Okay? So this is going to 0, which means it converges because it's less than 1. The ratio test, if you get less than 1, it converges. Greater than 1, it diverges. And exactly 1, you can't tell. You got to go find a different test.
Got it.
All right. Man, this chapter, I tell you what, even after a year of working on this chapter, it still gives me anxiety to even look at some of these problems.
And then I got 8C, perfect, 9A, perfect, and then 9B I got half right.
Oh, I didn't know there was another one. Is there another one on this?
There should be.
Whoops. Let me open that. Photo 3 again?
Oh,
thought
that should be photo 2 of the second
no.
set, I think.
Yeah. Oh. The second page, there was no 9.
Oh, okay, then it should be photo 1 of the second set I sent you.
Photo 1 of the second set. It's up here. Yeah. Here's a 9. I hadn't seen.
So I got the first 2 of that page right.
Okay. So you got the radius of convergence by using the ratio test. That comes down to the limit of 3x as n goes to infinity, which means all x.
And I did the interval test as well.
Hold on. No, not all x. Then it means that that thing has to be less than 1.
Yeah.
Okay, which is what that says. And then so your radius of convergence is that, okay? And which one did you want help on? B?
That one, right there.
All right. We're finding the radius of convergence. So it comes down to 2x minus 3 over 6. As n goes to infinity, so therefore that has to be less than 1. 2x minus 3 has to be less than 1.
I didn't know what I was doing on that one. I don't
Looks
know.
like you haven't taken the 1/6 out. In other words, could it be that you only got 2 points because you didn't carry the 1/6 forth?
Well, is that all I did wrong?
Well, I think so. In other words, what I can write at this point is that let me think for a second. So if my limit ends up being 2x minus 3 over 6, if I don't take that 1/6 and factor it out, and now I say that has to be less than 1, which means that has to be greater than minus 1. So there's the only thing you did wrong, because you didn't have a 6 in the denominator. That is going to make a difference, because that means that we're now going to go from 6 to -6. And now we're going to add 3 to both sides. So we're going to go, and now we're going to divide everything by 2. So the interval of convergence, I think, is that. -3/2 to 9/2.
Yeah, that looks right.
All right. Do you have answers on these?
We looked over them briefly, but I don't have answers written down.
Okay. Well, I think that's the way you do that one.
That looks right to me. I'm gonna write this down.
Yeah, it feels right. Feels right to me too. Yeah.
And I got to that part and I ran out of time.
Was there more?
Yeah, there's one more page.
One more page. Wow.
Yeah, it was a really long test. We only had 45 minutes.
45 minutes for all of this. Wow.
Yeah.
That's tough.
It was brutal.
That is brutal. All right. Anything else tonight, Emily?
Do we have time for the last page, or if
well,
not, it's okay.
Send it to me and let me look real quick and see how hard it is.
You have it. It's page 3 of that. No, it's page 2 of set 2. It's, I don't know how hard it is. I didn't get a chance to look.
Is that somebody's name?
I have no idea.
Past AP question. Huh. Taylor series about x equal 5 for a certain function converges to f of x in the interval of convergence. The nth derivative is given by that. F of 5 is that. Write the third degree Taylor polynomial for f about x. Okay. What's the first derivative going to be? In other words, in order to write the third degree Taylor polynomial, I'm going to need f of 5. I'm going to need f prime. I better write it underneath. And I'm going to need f double prime of 5 and maybe f triple prime of 5. Okay? So this formula right there is telling me f prime of 5, I'm going to substitute 1 for n and 1 for these n's. So the first derivative at 5 is going to be minus 1 to the 5th times 5 factorial, all divided by 2 to the 5th times 7. So it's a negative number. That's your coefficient of the second term. Let's see, f of 5 is 1/2, so we can start building this series. So my series is going to be 1/2, the first term, plus, that's a negative number, so it's negative, whatever that is, it's 5 factorial over, ooh, hold on a second. Yeah, over 2 to the 5th times 7 times x minus 5. Okay? You with me? How to finish the rest of it?
Yeah.
In other words, you need to figure out the coefficient of the next term. And you're going to do that by taking the second derivative and substituting 2 for n. And that will give you a number. And that's the coefficient. So I can see it's going to be positive. So it's some coefficient that's going to look like this. And then it's going to be times x minus 5 squared over 2 factorial. And that's going to be the third term, I guess, based on our understanding of it. That's 1, 2, 3. So the only thing missing here is this coefficient. In other words, plug in 2 for n and whatever number you get here. How did I get 5 factorial? Man, this whole thing is screwed up. I didn't do that right. You see what I did? I substituted 5 for n instead of 1. This is the first derivative, so it's 1 for n. And it's over 2 times 3. So that first coefficient, this one here, that I really mangled, is actually 1/6.
Okay.
And do you want this coefficient here?
That'd be great.
So that's f2 prime of 5. Notice the 5 doesn't have anything to do with evaluating what that coefficient is. There's no x in there. So it would be minus 1 squared times 2 factorial all over 2 squared times 4. So that becomes positive. 2 factorial takes out one of those 2's, and I get 1 over 8. We still have the 2 factorial from this, though, that we have to leave there. So in essence, I get 1 over 16. That should be the third degree Taylor polynomial,
Okay.
centered at 5. Find the radius of the convergence for that series. Wow. How am I going to find the radius of convergence? I don't know how to apply the ratio test. I don't have a function. I have a series. I have the first three terms of the series.
Could we do a...
Well, what's the series going to be? Let's see if we can define what the series is. Because if I can list the series, then I can apply the ratio test and we can go through our process to determine the radius of convergence. What is this series? It's got to look something like that. In fact, we know it's an alternating series. We know that there is an x minus 5 to the n. And we know the denominator now, the question is does this give you this? When we put 0 in there, we get 1/2. When we put 1 in there, we get this. So this indeed is the series that we just created. So now we can apply the ratio test. So let's see, I'm going to do x minus 5 to the n plus 1 all over 2 to the n plus 1 times n plus 3 multiplied by this series' reciprocal.
Wait, why do you ignore the negative 1 n?
Well, you just do. In other words, that's not the series. The series is actually that. If I'm going to say a sub n is something, it's that.
Okay.
Okay? And that's all I know. I've asked that question of myself before also, and they never include the minus 1 to the nth. They never include the alternating aspect of it. So let's see, what do we got here? The n plus 1 goes away, that goes away, that 2 to the n over 2 to the n plus 1 must be 2 to the 1. So now, the limit of this as n goes to infinity is 1/2. Right? The coefficient of the n is 1 up here, it's 2 down here. So if I'm looking at just the n's, it's 1/2. What the heck do you do with one? Let me look in my book and see if I can find one where they have to figure out that limit where there's an x and an n in there. Let's see, what are we doing? We're finding the convergence, radius of convergence. Which chapter is that? Intervals of convergence. Okay. No, I need to go. Just a second. got one here in the book that looks kind of similar. That should help us. When they get to the point where they say the limit of, and the one in the book is n squared x all over n plus 1 quantity squared. Well, the limit of that as n goes to infinity, notice that the ratio of the coefficients of the n, that's going to be an n squared, that's an n squared. So this part of it goes to 1, which means the limit of this whole thing goes to that.
Okay.
Which means the limit of our thing goes to that. X minus 5 over 2. So I would say that x minus 5 over 2 has to be less than 1. And that's going to give us our interval of convergence. X minus 5 is less than 2 or greater than minus 2, which means our interval of convergence is 3 to 7. No, what am I doing? Yeah, 3 to 7. Now, we don't know about the endpoint yet.
We don't need to, though, because it's just the radius of convergence.
You don't need you didn't ask about the interval of convergence. Yeah, okay. Well, I think that was the radius of convergence.
It is.
Okay, good. And the last one, what do we have more here? Is that it? No. Show that the 6th degree polynomial for f about x equal 5 approximates f of 6 with error less than 1/1000th. I don't think we have time for this one.
Okay.
Not sure I know how to do it, but I would have to look it up. There's an example in one of my calculus books that does a problem like this, and I would just have to look at how they did it and try to do this one the same way.
Okay.
Okay?
Thank you.
You're welcome. And still Friday at 3?
Yes, please.
Okie dokes. I will talk to you then, Emily. Have a good
Thank you very much.
tomorrow. Bye-bye.